Hi, class. Lecture 8, Recent Advances in Perception. The outline of today's lecture is as follows. I'm going to introduce you to three topics. The first one is Tesla AI Day. I'm going to give you introduction to um, their AI Day video that's available online. This is actually part of your homework number one. But I will give you a brief overview of the video. You should watch video closely. And then I'm going to introduce you to two research works. One is camera radar sensor fusion, and then the second one is self-supervised learning work we conducted. Right, Tesla AI Day. Like I emphasized during the discussion session last week, you should watch the video multiple times if your research area is autonomous driving. Um, there are you will be able to find many videos online. Um, Tesla actually presented their official uh, AI Day. They had two AI Day videos officially online. And then they also presented in uh, AI workshops like CVPR and other workshops. And you will be able to find some of the workshop videos online too. So if you're interested, you should definitely watch those too. But we are going to go over the AI Day videos here, especially the perception part. But there are many other parts that you should watch as well. So it starts with sensor specification. They have 8 cameras, 1.2 megapixel, 360 field of view, 36 frame per second, no radar, lidar, ultrasonic. Um, but the camera and the NPU board, their computer for the hardware for FSD has been evolved over time. So this one is a relatively old specification. Okay. If you look at the intro overview of FSD, you will be able to see this slide. And you can see there's a training data module at the bottom. And then there's a training infra on your left side. And then there's a AI compiler and inference. Um, and then in the middle, they have neural networks, which has two parts, occupancy and lane and objects. Basically, the occupancy is a 3D feature based um, pipeline architecture, whereas lanes and objects are bird's eye view based features and architectures. And then result of that is connected to a planning module. Okay. Cameras, Basically there's eight camera inputs. There are three cameras, forward-facing cameras, wide view, standard, and zoom. So they have three. That's three forward-facing, and then all of that goes through the neural networks, and output is three-dimensional vector space uh, containing lanes and objects. Okay. Note that they do talk about this camera calibration. Um, as we briefly talked about this earlier, cameras are different from model to model and vehicle to vehicle. So there's so in order to achieve consistent perception and autonomous driving performance, we do need to take care of this variations in camera calibration. So what they introduced was this rectify layer before the network. So they introduced this concept of common virtual camera. So what they are doing is basically they have raw data input coming from the camera, and then they go through this undistort and rotate and distort to a common virtual camera perspective. So it's consistent over um, all models. And the next slide shows from here on, we're going to talk about spatial temporal backbone. So, which starts with 2D feature backbone. So it's basically CNN, uh, neural network backbone, which extracts 2D features from the images. Um, this is done for each image. So we have eight images. So we of course we share this network, but each image um, is processed through this 2D feature backbone. And then what one noticeable difference from academic network is this multi-scale feature pyramid fusion. So this is very advanced uh, level of, you can think of this as feature pyramid architecture, but in multi-scale, and tries to fuse this multi-scale feature um, pyramid, so that we have the neck and head can actually have access to these multi-scale features. And then it goes through this spatial fusion, which uses attention. This is very similar to uh, BB um, but it just uses different, um, probably larger model with this bidirectional feature pyramid network, multi-scale features. Okay. Notice that there's a positional encoder, there's pooling, MLP, Those are all used along with transformer. Okay. And then there's a temporal fusion, which Tesla calls video module. They have two layer. One is feature queue, which simply uh, concatenates all the features, temporal features, and then put that into video module. The video module uses RNN instead of attention or transformer. Um, so please note that uh, Tesla uses RNN to handle the temporal fusion. And if you watch the video, they actually considered uh, all three options: 3D CNN, transformer, and RNN. And they decided to use RNN, but note that they call it spatial RNN. Okay. And then the spatial RNN is a bit different from just regular RNN in a sense that they're using this RNN unit for each space rather than whereas usually existing RNNs represent sequence or time sequence type of uh, signal. But here, uh, this RNN module is dedicated for each space so that it can do this type of mapping um, functions. And by using this temporal fusion module, video module, it can handle occlusions and can predict, can estimate the velocity of vehicles that are around you. This is very important in traffic situation because you need to compute how fast vehicles are approaching um, to avoid collision or to make proper decisions and plan your motions. Okay. And notice that they have multitask header. So here they're showing three head object detection test, traffic light head, and lane prediction. Let's talk about lane object first. Lane is basically mapping, but focuses on lanes. So center line and then road boundaries, um, and then where the lanes are. Those are covered by lanes, basically mapping. And then there's objects, vehicle, pedestrian, all kinds of objects needs to be detected for driving. And prediction is also covered by this object head. And this is the architecture. So note that they have this transformer, which takes care of the spatial attention, and they have the queue, so concatenates, multiple BV features, and then put that into video module, and that feeds into detection head. So you can, and then it'll detect, you know, objects. And note that that is used to um, to convert this large 3D tensor into um, more dense um, you know feature set feature set using these masks. Um, but I wonder why they call it sparsification. I'm not quite sure, but they originally they had this sparse tensor, and then the detection head uh, detects objects, and then use that information to extract features, and they call it sparsification. By doing this, they can have multiple um, agent agent attributes. More uh, kinematic information can be extracted from this feature set. Okay. And next, let's move on to mapping. Um, Basically, the here we are talking about online mapping, so we don't use HD map. We don't use offline map. Instead, we need to map um, on the fly in real time based on image input. And this is quite tricky because this is quite different from 3D object detection, localization problem. And in order for autonomous driving work, we definitely need to have map lane information so that we can drive and follow the lanes and road rules. Okay. Um, this is the architecture they shared um, at AI Day. After video module, they have this map component which shares navigation map, and they have lane guidance module, and then it outputs some tensor um, feature set, and then that feeds into this language component, which is autoregressive decoder, and it outputs lane instances and adjacency matrix. So how lanes are connected and the relationship between links. Um, and they actually spend some time describing this lane net. So please make sure you watch this video. Okay. Um, so this is, like I said, this is part of the homework, and I'm not going to go through in detail here. Okay. But remember, they do use this um, autoregressive decoder, and it looks inside of that module looks something like this. It has vector space encoding, goes through some attention, cross attention, self attention to predict point, topology, fork, merge, spline. Okay, so the final output needs to look something like this. Excuse me. Next part is going to be occupancy nets. Like we introduced during the lecture, previous lectures, if you only use, you know, object detector, 3D object detection head, it's difficult to handle all kinds of, different different types of objects, unknown objects, and deformable objects, very non-regular type of objects. So occupancy network is utilized to handle these challenging objects to make sure it doesn't collide with these objects. Occupancy network looks a bit different from the lane and object network. Um, up to up to video module, it's same, but note that there's this deconvolution layer, and it gives two outputs, surface output and volume outputs, and volume output is what's used for the occupancy head. Okay. Okay. So that covers most of the architecture part. Now let's talk a little bit about their data engine and auto labeling. Um, in this course, in the perception module, we talked a lot about architecture, model architecture, but in practice, in reality, data engine is, so much more important and challenging, critical to achieve actually working model because it's all about data dependent. AI is you know data dependent uh, system. So to to obtain data set, we need to achieve full autonomous, fully self-driving uh, vehicle. We need this type of data engine. What happens here is that basically, let's say you collect data, you label data, and you train the model using the data set, and then you're going to deploy to Tesla fleet, and then um, these, fleet vehicles will, drive around over, you know, over the world, and in theory, they can actually collect data using shadow mode. What it means is the inference, the model runs in an open loop manner. So the output of the model doesn't actually is not actually used for driving the car, but it's running um, like a shadow, or sometimes it's also called a ghost mode. And by doing that, we can tell a lot about the scene the vehicle is experiencing. And you can use that to, trigger, uh, the memory to store the data and then send it out to the cloud for Tesla, and then they can use it for uh, for constructing their data set. Okay. So it runs, and then using that data, they can further you know further mine similar data from Tesla fleet, and then that's often called a boost, data boost, and then they can also create some evaluation data sets to evaluate performance for that type of data. So it goes through this cycle. So it's called they call it data engine. Sometimes people call it data flywheel. Okay. Um, so this slide is basically showing how they collected data over time, and the data increase, size of the data set matters when it comes to performance. They also talk about auto labeling. Basically, to train the model, you need to label everything. You need to label lanes, objects, occupancy, right? And many of these attributes, object attributes, but they actually spend significant time on auto labeling uh, the lanes because it's one of the challenging labeling job. Um, so and please watch this part carefully, okay? And you will see they have three parts. First step, they use traditional computer vision techniques to find high precision ego trajectory. So that basically it's a slam technique to find both ego trajectory as well as um, surrounding information, you know, mapping the surrounding information. And then they go through this second step, which is multi-tree reconstruction. Um, they actually had uh, multiple types of auto labeling technologies for their system, and you will be able to find how they evolved over time if you watch video. Okay. All right. So that's it for Tesla AI Day. So this is a very quick summary of AI Day. So make sure you watch a video and complete your homework. Okay. All right. Camera radar sensor fusion. Um, if you look into how sensor is configured for uh, yeah, ADAS, advanced driver assistance systems, they do not use LiDAR. Instead, they use radar. Um, Radar is a very strong, very good sensor for light and weather conditions and for long distance detection and detecting velocity. So radar does have good features. compared to other sensors. And it's not as expensive as LiDAR. So many of the mass-produced vehicles are equipped with camera and radar. And if you take a look at this video clip, this is uh, you know how vision, camera object detection performance, uh, performs. Of course, this is a bit old. Um, can you see this is a KAIST campus? So this we recorded this video um, ourselves. You can see the object detection performance is not so great. It's not perfect. And if you take a look at this one, this is radar performance. Again, this is our own recording recorded in KAIST campus. Notice that if you look the figures on the right side, notice that the radar object detection results are very noisy in the angular direction. So, and that's because the way automotive radar is designed, it's not scanning type. Instead, it uses this array of antenna to distinguish this angular positions. But the resolution is not so great, so it's very noisy. So as you can see, camera is good at angular um, angular position, angular values. Radar is good at longitudinal, radial values. And camera is sensitive to weather, lighting, but radar is good at weather and lighting conditions. So it's very complementary. So early, like 4 years ago, 4 or 5 years ago, we started to investigate into radar camera fusion, and this is how ro radar works, radar signal processing works. It emits active signal, and then reflected signal is received by antenna, and um, so that is going through this you know ADC sampling and fast Fourier transform to get this 2D range Doppler image, and then 2D range azimuth information. And using those information, we can get this point cloud with velocity information. And doing some more signal processing like clustering, tracking, we actually get the final object level detection results. Um, but it, but radar camera fusion has been out there for a while. But most of the camera radar fusion was high level or late fusion, meaning that there is two different pipeline for camera and radar. It was done this way because they so you know the technology was developed separately. The camera vision was developed by Mobileye, back then. Um, and then um, and then radar was developed by other suppliers like Continental, Bosch. And so because they have two different supplier, automobile manufacturer had to do the fusion, high level fusion, based on the signals that you get from Mobileye and signals that you get from radar in object level or point cloud at best. But if you do, if you use this type of high level fusion, then you're not actually getting the full potential out of the fusion, the full potential of the camera radar fusion, because a lot of the information is lost during this you know separate pipeline. Um, and when you fuse at high level late, then it also creates other problems. For example, if they don't agree, if radar says there is no object, but camera says there is an object, then how would you go about it? Well, we want safety, so we want to be more conservative. Then we would say there is an object, right? But what if the camera was wrong? Then it becomes false positive, right? So and it's going to introduce like um, ghost braking or you know, you know, for example, braking, although there's no objects, okay? And this is, you know, people wouldn't like it very much, right? It's not acceptable. So we wanted to investigate into low-level fusion, but how, right? There were no uh, fusion work, um, back then. And one of the high-level fusion we um, worked was this. Uh, so we use radar detection results for the radial information, but the lateral information we used it um, we used part detection. So here in this example, we used a small, small CNN backbone and neural network to detect vehicle parts, especially focusing on corners, bumper corners. Like, is this left corner, right corner? So we can tell angular position of that vehicle. So this is quite old work, um, you before all kinds of advanced CNN vision work and attention was there. Okay. Yeah, this is introduction or motivation for low-level radar vision fusion. And this is the architecture we introduced um, a while ago. This was one of the first early work in history that fused radar and camera uh, using low-level fusion for both radar and image features. And we used cross attention to fuse radar feature and image feature. So of course, we had to align the space in bird's eye view, and then fuse. And then the fuse feature is used for mapping and detection. Oops. And you're looking at imaging feature, radar feature, and fused feature at the bottom of the slide. This is qualitative results. You can see we are comparing camera versus radar camera fusion and LiDAR. Okay, and you can see camera radar fusion gives better detection performance, especially for long distance objects. And we also looked into how fusion network performs in rainy and night scenes. And clearly, camera radar fusion was providing better performance uh, in rainy scenes and also night scenes. This is quantitative results. We compared our model, which is CRN, uh, which fuses camera and radar, and we compare with different, you know, modes, camera, fusion, and center point, LiDAR detector, and it was close to LiDAR detector. So we were quite excited about this work, and it was uh, ranked first on the radar fusion leaderboard. Um, but of course, the society evolves over time, and I believe that's now um, there's better outperforming models now, right? This is just to show we tried to we collected our own data set for even lower level radar fusion, such as uh, this heat map. Um, but previous work was using point cloud, using nuisance data set. Okay, let's move on to last part, which is self-supervised learning, 3D feature pre-training. All right, why self-supervised learning? Well, um, labeling cost is um, unreasonably high. Think about how much Tesla had to collect over time. And unlike many other domain, to collect data, we have to build, this vehicle equipped with the sensor. And then you actually have to drive around in real world and collect data. And then you need to, go through this, filtering, cleansing, and selection process, and then you annotate and then train. All this process is quite, resource heavy, but annotation is especially expensive, especially think about, um how to label this map and how to label uh, 3D occupancy, how to label 3D objects in 3D space. In the early days, human annotation was required. Um, but as AI model evolves over time, and if you use LiDAR, then sometimes you can use LiDAR detectors to um, to auto label some of these tasks. But still, this whole data engine and this, you know, labeling and process are quite costly. And think about expanding this to nationwide and then global wide. Okay, so to avoid this data dependency and data cost. Oftentimes, self-supervised learning is used for pre-training, um, and usually, self-supervised learning works like this. So we have unlabeled data, and uh, you use some kind of pretext task. So without labeling. So by doing this, you can learn this representation H feature set, and then you can put your downstream tasks and then fine tune or you know post training um, to achieve high performing um, network using labeled data. So this was very successful in language and 2D image. Um, it was, it actually started from language um, for sequence problems, and they actually masked. It was very natural because if you think about it, you actually don't need labeling. You already have ground truth if you have text because um, but by masking some words, you can pre-train um, the model, uh, the feature extractor backbone, and then you can you can add some downstream task to fine tune and adapt to get the output you want. And this turns out to be very successful. And this is called mass language modeling. And this approach was expanded to image computer vision, and it's called masked autoencoder. So same concept, same idea. So you use image and then you mask some parts, but because you already have the ground truth, you can use it as a target or output results. And by learning this type of self-supervised manner using this pretext, this is basically like playing playing game or solving some quiz. They were able to learn this representation, relatively robust representation. Okay. But for our problem, many robotics, including autonomous vehicles, it's not trivial. It's more tricky um, than these language and 2D images because our input is 2D, but our 3D our feature we the feature set we want to train is 3D feature. So whether it's a bird's eye view or 3D tensor voxels. Okay, so how do we obtain 3D info? So which is related to pretext, right? Um, and luckily, I think like 5 years ago, neural radiance field nerf work came out. The this was novel view synthesis work, which means if you have multiple input images and you can train model using these images, and then you can actually render new views because the model learned um, the actual how 3D this object is shaped in 3D space. So it was able to render new views. And this was quite impressive work back then. And then, of course, 3D Gaussian splitting came out, which turns out to be much more efficient and faster. And there were work try to use this self-supervised learning um, for 3D perception, autonomous driving. It's a Uniped. One of the early work is Uniped. But it was early work, so it definitely it poses academic contribution, but it was simply adding this nerf network as a pretext task. So if you take a look at this pipeline, we have image input, and then um, this is, let's say this is 2D feature set, and then go through view transform, and then we have voxel, tensor, 3D tensor feature set. And then we add this nerf network, which um, basically renders RGB and depth from this 3D uh, feature set. Okay, so what's happening here is to make this 2D this 3D perception network learn using self-supervised learning. What's happening here is that our input is 2D, right? But we also want to use it for output, right? So what needs to happen here is that 2D input, and then we want 3D feature representation, and then back to 2D. So that's what we need to design here. 2D input, 3D feature, and then back to 2D output. So that's what's happening here. And Unipad, like I said, introduced this nerf network to render 2D image RGBD from 3D feature 3D feature set. And then after pre-training, after self-supervised learning, um, it now we can apply fine-tuning um, for downstream tasks, um, such as mapping or 3D object detection, 3D occupancy, right? So we add that kind of head, 3D perception head, and fine tune. And it turns out it helps a little bit. Um, there are two reasons. It was not um, very substantial because I think there are two reasons. One is these academic work uh, didn't have large pre-training data set. And second, um, we are learning 3D representation from 2D images only, right? So so 2D to 3D. So we basically what we are trying to do here is learning 3D feature from 2D images, right? So it's a ill posed problem. It's not trivial. Um, so for those reasons, 3D self-supervised learning in 3D perception is pretty challenging problem. Um, our lab also wanted to push this forward to the next level. So what we proposed was so previously they used this nerve network, and then for actual fine tuning, we Uniped had to discard this nerve network part, the pretext network, and then used a different head. So they were hoping that the view transform was learned from this pre-training process, but this is a bit far from the rendering head, the final loss computation. So the gradient in view transform will probably become small. So and and then we are discarding this whole network, right? Which we pre-trained. So what we propose in our lab was a new network architecture. So why don't we just directly use this nerve network um, as uh, as a sort of view transform, and then basically uh, directly use that network for the all the way for the inference pipeline. So we don't discard uh, you know this main network. This is the architecture. So we have this 2D backbone feature, and then we use deformable cross attention, where for pre-training we use nerve type of sampling, ray-wise sampling, and then learn RGB and depth. So we train this attention network, and then for fine tuning, we use this downstream task using uniform spatial sampling in query, so that it can fine tune for the task we want. Okay. And this is the pre-training results. The left video is ground truth. Right video is 3D occupancy prediction. Note that this is pre-training only. we did not use any supervision, any labels here. It's not great, but it still, outputs some 3D occupancy um, results without any supervision. And this is RGB depth reconstruction results. We compare that with Unipad, Self-OCC, and NERP 3D is the proposed or network. And you can see Unipad was not doing great when it comes to RGB D reconstruction. And we think that it's because it's using voxel discrete uh, discretized feature set, and then the nerf is actually trying to learn the continuous 3D space, but it's discarded. Um, and so this is one of the early work, and self OCC actually improved that little bit, but still not great. But if you look at our work, NERP 3D, the rendering, the RGBD, and depth reconstruction is quite good compared to GT. Okay. So dataset, nuisance dataset was used. Metric was for pretext, there's RGB rendering and depth rendering. And for downstream task, 3D object detection, 3D occupancy, and H mapping results. And some quantitative results are listed here. And you can see we were able to achieve substantially improved pre-training performance. Um, but it turns out that for downstream task, the gain was not so great. Um, but note that we are not showing the baseline, which is no pre-training. It's something like 35 some MAP. So so it's you know significant just by having pre-training, without labels. So it actually helped. Okay. So this is it for today. Um, um, and I apologize for the delayed video upload. But I hope you find this lecture interesting. Okay, see you in class in discussion session. Okay, have a good weekend.